Thank you for the introduction. It is my pleasure to present our EPA-funded AEROSOURCE project focused on identifying air pollution sources in Ireland, which later has devolved into a national aerosol mass spectrometry network. It was a collaborative project led by NUAG with international partners from Italy and national collaboration with UCC. The link between air pollution and health effects has long been acknowledged, with WHO describing air pollution as the single biggest environmental health risk, causing over 5 million premature deaths per year worldwide. But this is not a distant third world problem. Close to 500,000 premature deaths occur each year in Europe and over 1,300 in Ireland due to air pollution. The link between increased black smoke concentrations and a greater death rate in Dublin has been shown by Irish scientists for 1980s events already. This prompted several legislations, with smoky coal ban in Dublin in 1990s being one of the best known that noticeably cleaned up Dublin air, and has since saved approximately 8,000 lives. Besides, emissions, especially from power, transport, and industry sectors, have been the focus of policy development. Measures such as introduction of strict emission standards, fuel regulations, and after-treatment like end-of-tailpipe particle filters have been widely deployed with great success. And our data record reveals around 80% reduction in airborne sulfur pollution over the 35-year period as a result of these legislations. So why do we still see headlines like this from the last year in Irish Times, pointing to bad air quality in Dublin not being the thing of the past? Could it be that different sources and compounds contribute to air pollution that were not highlighted before? From our measurements, we see that carbonaceous compounds, organic matter, and black carbon combined now dominate the PM composition, both in Ireland and worldwide. And these are much more difficult to monitor, thus not routinely measured in standard air quality networks. Moreover, sophisticated emissions reduction strategies informed by next-generation observation networks are required to identify and tackle the largest culprits. Motivated by this, and to support the new National Ambient Air Quality Monitoring Program, we have established a network of 4 aerosol mass spectrometers that simultaneously run in several selected locations, from short-term campaigns in Birr, Mullinhead, or Galway, to long-term measurements in Macehead and Dublin. Aerosol mass spectrometers are not only capable of measuring PM mass, but provide real-time chemical composition, including aforementioned organic matter, and even more importantly, provide basis for further source apportionment to identify main air pollution culprits. The network was first established under the EPA-funded AEROSOURCE project and now continues as a national network. The network runs in 3 permanent, specially selected sites: Macehead for marine natural background, Carson Point for quantifying long-range transport from Europe and UK, while Dublin UCD site enables categorization of local urban air pollution sources. In its first 3 months, the network has revealed a series of extreme air pollution events in Dublin that were dominated by organic matter, the green color in this picture, that would not otherwise be characterized by standard monitoring instruments. The concentrations in these events have reached 300 micrograms per cubic meter, and daily PM2.5 levels have exceeded WHO recommendations 1 in 5 winter days, 17 in total for that particular winter of 2016 and 17. And this was considering the old WHO guidelines, while the new, stricter ones released recently would result in even higher number of exceedances. Just to put this into perspective, the PM concentrations in Dublin were of the same level as the ones in Beijing over the exact period. So even if Ireland's air quality is relatively good overall, Owing to prevailing marine air masses coming from the North Atlantic, the winters are not so clean after all. The aerosol mass spectrometry has also enabled us to look for the main culprits of these extreme air pollution events, and to our surprise, peat and wood combined contributed over 70% of PM mass in Dublin, with similar picture revealed for winter averages as well. Heating sources come on top of background air pollution concentrations that combine traffic, long-range transport, and secondary aerosol production. The absolute PM concentrations for traffic remain pretty constant over the seasons, with relative contribution increasing over summer due to absence of local sources. In conclusion, the secondary or supplementary home heating sources like peat and wood burning due to their higher emission factors contribute little to the city's energy budget, but are the main culprits for the extreme air pollution events in Dublin. And this is not exclusive for Dublin. Major air pollution events over all Ireland are mostly caused by peat and wood burning, with lower contribution from coal or oil. You can see that contributions on the right column here in the graphs, and see that the orange color dominates the concentrations in different locations in Ireland. But okay, one can say that this is a feature of residential locations. What about congested streets? We went there as well, or rather brought our ACSM to a curbside of one of the busiest streets in Dublin, Pearse Street. The differences in composition were obvious straight away, with black carbon, gray color in pie charts dominating the composition, as opposed to organic carbon or the green color in the pie charts in residential Dublin. But combined, as I mentioned before, the organic carbon and black carbon, the carbonaceous compounds were still the major contributions to the mass in both locations. A source apportionment has also indicated a large variety of sources acting at the curbside, with the aerosol coming not only from traffic, depicted mostly as gray HOA that also combines all heating, but large contributions from cooking and secondary production, especially during non-heating period. For this period, the absolute concentrations in the curbside are also significantly higher than the ones in the residential site. Note that this is concurrent measurements in both sites, so measuring at the same time, exactly the same period, and the y-axis are of this exactly the same scale in all the graphs. But the heating period reveals a different picture. All non-heating sources are swamped by the solid fuel burning in both locations, and the diurnal trend in the curbside does not follow a standard bimodal traffic peak with morning and evening rush hours superimposed by lunchtime cooking peak as it was during non-heating period. Now the evening peak spikes occur simultaneously in both curbside and the residential areas. But in order to be able to separate those different fuels in ambient atmosphere, we first had to perform some lab experiments to fingerprint them. We used locally purchased fuels and 3 types of stoves, from open fire to eco-type stove depicted here, and the sophisticated setup of multiple instrumentation, online instrumentation, not only has provided fingerprints and chemical composition of different fuels, but enabled us to estimate mass and number emission factors. While the experiments have confirmed a reduction in mass emission factors with fuel treatment, as emissions have reduced when going from wood, smoky coal, and peat to so-called smokeless coal and biomass briquettes, indicating the lower contributions to mass concentrations from the latter fuels. The number emission factors, however, show quite an opposite trend, with process fuels emitting smaller but more numerous particles confirming a complicated picture of domestic heating, especially when it comes to human health. The importance of particle size in health effects is shown in the deposition efficiency of different size particles in human respiratory system. Some particles, like the ones around few hundred nanometers, can enter the system, but also exit without doing a significant damage, as they won't be retained there. So we would inhale and exhale the particles without experiencing any effect. When we apply the knowledge acquired in our laboratory experiments to source apportion ambient aerosol concentrations, interesting differences between sources contributing to mass and number became apparent. Where peat, wood, oil burning with traffic dominated the mass concentrations, with smokeless coal or biomass briquettes being almost indistinguishable, while the latter dominated the number concentrations of particles. As mentioned before, due to smaller particle sizes that are emitted from smokeless coal or biomass briquettes, they do not contribute much to the mass, but can still contribute significantly to particle numbers in ambient air. Finally, applying the deposition efficiency shown on the left to the graphs or pie charts shown there, in human respiratory system, we can see the sources contributing to numbers might as well be the ones affecting our health most. These are pretty new findings, so require further investigation to properly quantify the effects. In addition to size, the composition of particles is also extremely important, as some materials like sea salt that we have plenty of in Ireland would not be equal in their health effects as some nasty organic matter mixtures. For this, we have looked into the oxidative potential or oxidative stress of different sources or different fuels that can be assumed to be acceptable proxy for the toxicity. I mean that the oxidative stress can be a good proxy for the effects of the different sources on human health. And we negated the perception of harmless green fuels, as wood and peat contributed most to the oxidative stress in residential Dublin area. This again requires further studies, but preliminary results do indicate that peat and wood are natural and harmless as long as we don't burn it, while any burning process produces harmful particles that cause negative health effects, shown here as the oxidative potential or the toxicity of the sources, which I hope were also highlighted in the previous talk by Colm. Finally, our state-of-the-art air pollution forecasting model had to be updated with these secondary solid fuel burning sources that were not captured by the most recent emission inventories, including MAPAIR, resulting in model missing most of the pollution events, the black line here in this graph, and pink representing location or the ambient measurements. While after parameterizing the supplementary burning emissions to temperature and accounting for different emission factors, model has been able to capture the time and duration of these events, the blue line. So the black line without the adjustment of the emission inventories, and the blue line, the model results with the adjustment or parameterization of the secondary solid fuels. The remaining differences in absolute concentrations are mainly due to comparison of the point measurements in UCD, so one location, versus a model which covers the grid cell of 25 over 25 kilometers, which in practice is almost the whole city. To finish my talk, I will raise a question to think about whether one-sided policies, like the ones focused on tackling climate change problems and reducing CO2 emissions, that still promote biomass burning, which luckily happens less and less in Ireland, but not replicated in the rest of Europe, damage our air quality. Therefore, we have to promote and support so-called win-win policies that account for both climate change and human health or environmental effects. Last but not least, I'd like to thank our funders, and this would not happen without the support from the EPA or the Department of the Environment, Climate and Communications. Thank you, and I leave you with this slide. And if you have any questions, please post them on the app.